Okay, welcome back to this other topic of this intensive course. So this will be about exact sequences. There's not an immediate relation with what I talked about with tensor products before, although tensor products will provide examples at some stage here. So as you can see, we'll be following essentially section 1.6 of Iko Moerdijk's lecture notes. Again, there are many other places where you can find this or this terminology. Again, for example, this book that I mentioned, Dublin Foot, Abstract Algebra, 3rd edition, will also have, will also discuss exact sequences, and the thing will be discussing with many, many more details and examples than Iko Moerdijk's. But this is a common subject, will be many good books to look at. So let me say what our context will be. So let me first say that if we have a morphism from A to B of R modules, and before with the tensor product I was very specific about what should be a left R module and what should be a right R module. In this case, the only thing I really want is that they're the same. So both A and B are left R module, or both A and B are right R module, and then you can do the same thing. So let's just think of left R modules because that's what we're usually working with. So then we have few modules associated to this, and there will also be R modules in the same type, so left or right depending on what we started with. And we write them here. So we have the kernel of phi. We have all A and A with phi of A is the 0 of B. Let me write this in this case. We have the image of phi. That is everything I can get out of phi by applying it to everything in A. And this here will be a sub on R submodule of A. And this is an R submodule of B. And then we have another one that we may or may not use very much, but let me just recall it. You can also look at a co-kernel of phi, and this will be B modulo the image of phi. So this is a quotient module of B. Okay, so let me start with the definition now. Suppose I have a sequence of R modules and morphisms of R modules. So it will be a sequence. And it can be, well, it could be a finite length, it could be of infinite length to the left or to the right or both. So let's start with an AI plus 1. And then we're going to map to AI. And then we're going to map to AI minus 1. Dot, dot, dot. And this first map will be phi I plus 1. So the index corresponds with the index that of the source. And here this will be phi I, and of course here is a phi I minus 1. So a sequence of R modules is called exact at AI if the image of the incoming map, image phi I plus 1, so that's the submodule of AI, is exactly the same as the kernel of the outgoing map, phi I. It's again a submodule of AI. So they should be the same. And the whole sequence is called exact. If it is exact at all the places. So if it is exact at all AI. Okay, one should take this with a little grain of salt because of course we can only talk about exactness at AI if I have both an incoming map and an outgoing map. And if that is not the case, then we ignore such places. So as a very simple example, let's look at the sequence right down here. Okay, so those will be a sequence of abelian groups of Z modules. So the first map here will be multiplication by 2. So the image in here will be all the even numbers, and this is the natural quotient map, and the kernel of this map is exactly indeed all the even numbers. That's exactly the image here. So it will be exact here. Now exactness here, this means that I look at the kernel here. Well, I don't specify the map because everything goes to 0. The kernel is everything, and that means that the image should be everything, should be surjective, and that's correct. Similarly here, for this one to be exact in this position, well, the image here is 0, so that means that the kernel of this guy should be exactly only 0, and that is the same as saying that it's going to be an injection, and indeed multiplication by 2 is an injection. Okay, so we have to check exactness at those 3 positions, and those 2 we just ignore because there is not both an incoming and outgoing morphism in those positions. So, in fact, such a type of exact sequence has a name. So a short exact sequence is an exact sequence of the following shape. 0 goes to some A prime, goes to some A, goes to some A double prime, goes to 0. So those are then R modules again over some fixed ring R. And here we have a map phi, and here we have a map psi. Those will be morphisms of R modules. And so it has to be exactly this shape, length 5, zeros at either ends. And that is the case. So just like in this case, well, the fact that this is image 0 means that this guy must be injective. So the first condition is that phi is injective. And the second one, well, this is the normal definition that the image of the incoming map is the same as the kernel of the outgoing map. So that means that we have the image of phi is the same as the kernel of psi. And as above, this has kernel the whole of A prime, so that means that this has image A, sorry, the whole of A double prime, so that means that this has image the whole of A double prime, and that simply means that psi is surjective. Okay, so writing down a short exact sequence is exactly the same as this. Now you can see already one obvious drawback maybe of this entire thing. You have quite a bit of notation. So for example, if you've given yourself a sequence like this, and you've specified the maps phi I plus 1, etc., then what you often do later on is you just write sort of AI plus 1 arrow AI, and then you just have to remember that the map has been defined before, but you usually, unless you really need it explicitly, don't write it down again in order to simplify the notation a little bit. Okay, so there are 2 more very short cases that one looks at. Okay, so example, if I just look at 0 goes to A, goes to B, so this is an even shorter sequence than the short exact sequence. So this is exact, well, there's only one position to look at, namely a position of A, and then we have again that the incoming thing is just has image 0, and therefore the kernel of this one should be only 0, so that means that this map A to E is injective. And notice that in this case I managed to avoid giving the maps the morphisms explicit names. Okay, and the same thing you can do on the right. So A goes to B, goes to 0 is exact. Well, just like before, this will be the same as saying that A mapping to B is surjective. Okay, again, I didn't specify anything, but all the maps are supposed to be maps, morphisms of R modules. Well, there are some very simple examples one can write down of short exact sequences, namely a direct sum sequence. So, example for A and B R modules. Then I can write down a very basic short exact sequence. I can look at the direct sum of A and B, and I can write this one down and let me specify the maps. So here I include A, so I take A and I give it the coordinate 0, B, so that's the inclusion. And here I take AB and I project this to B. And well, this is very easy in inclusion, this is very clearly a surjection. And the kernel here will be exactly everything that has 0 in the second coordinate, and that's exactly the image here. It's very clearly, exactly, you check very easily that all those maps, of course, are maps of R modules. And I could do the same way with the A and the B interchange, etc. This is not very exciting in some sense. On the other hand, if you are given a short exact sequence, so in that case there will be something else here that may or may not be directly this direct sum. And sometimes you want to recognize it, so it's actually a sort of criterion when something like this basically looks like this direct sum short exact sequence. So before we can say something about this, no, it's actually one, okay, we'll get to that later. So how do we recognize this? We're going to need a little definition for this. Suppose that I have A and B R modules. Then you say that A is a retract of B if there are R module homomorphisms I have to get the directions correct. So I want to have an S from A to B and R in the other direction from B to A, and I demand that if I first have S and I follow it on by R, so then I go from A to B and back to A, this should be the identity from A. So then S is called a section and R a retraction. Okay, you can sort of think a little bit in terms of errors, what is going on. So I have maps from A to B, and the map from A to start with B. This will start with B. So if I go from B to A, this will be necessarily surjective, right? Because from this I go from A to B to A, I get everything. So this will be a surjection, which I indicate by this double tip arrow. So that will be the R. And on the other hand, I also have a map which must necessarily be an injection, because it's this one here, it has a left inverse, and this is the S, and this must be injection, that's the section. Okay, they're of course related because of this property here, but that's what's going on. Okay, so let me state explicitly again that note that R is surjective, and S is not necessarily injective. Okay, so let's apply those notions to a short exact sequence and then see when this short exact sequence sort of looks like basically some exact sequence like this one. Proposition for a short exact sequence of R modules okay, 0 goes to A, goes to B, goes to C, goes to 0. And we have to give the maps a few names, so this will be F and this will be G. The following are equivalent. So it will be 3. A, this F has a retraction R from C to A. So that means that R after F is the identity on A. Okay, so I get a map from, excuse me, this cannot be right, this should be, I have interchanged C with a B here. I was sort of wondering when C is essentially A directs some B. Okay, let's try again. So F has a retraction R from C to A. So that means that if I first go from A to C and then back using this retraction, I get the identity on A. B, something similar here, this G has a section S from B to C. Okay, so it basically needs in either case a map in the opposite direction with a nice property. So that means in this case, if I first apply S and I follow it on by G, then I get the identity on B. And C, there is an isomorphism of C with the direct sum of A and B, of course, as R modules. Such that the sequence we have here, short exact sequence, let me first say is in quotation marks, is just the direct sum exact sequence. So this is the natural inclusion here and the natural projection there. What I mean by is, well, I basically want to say that we can rewrite the sequence a little bit. So more precisely, this is means there is a commutative diagram so I start with a sequence that I have been given. So this was F, this was G, and then I say C is isomorphic with A direct sum B. And then if I now identify C with this, well, I can get a map by just saying this is the identity on A with A. And if I go like this, I get a map from A to this one. Okay, this would have to commute. And I can do something similar with B. Okay, if I leave out this arrow, I get a map from here to here by going like this. And if I use that one, it should be commuting, but the point is that we want those to be the maps that we had in the original direct sum short exact sequence. So this is the natural inclusion, A goes to A0, and this should be the natural projection, A comma B goes to B. Okay, so there should be an isomorphism such that if I write it down like this, then this sequence here basically becomes, we're looking at the diagram here in between, the natural one. That's the real statement of C. Okay, let me give you a bit of the proof. Not too much because will be some details. But I'm claiming that if I take C, so I have a very nice sequence like this, and I want to check either A or B, so I have to get retraction, then I'm going to say this is clear in the sense that we should check it. Because I need a map from C to A with a few properties, and well, I have a very clear map here, because if I had this sequence here and I go from A to this one, then I can easily get my retraction by projecting back to A. And first putting A inside and projecting back to A is the identity on A. So for this one it's very clear, and suddenly if I look at property B, then I use the inclusion of B into this one and the projection back. And what you just have to do is translate those maps back into what you get at this level. Okay, so the map from here to here will be by going from C to here, projecting to A, and then going back there. And what you have to do, and that's the checking, is actually checking that what comes out is correct. Okay, so that's the exercise in introducing the notation and the properties. But beyond that, there's not so much going on. And the other two, so I would have to show that A implies C and B implies C. So let me do A implies C. So we've now been assuming that we have a retraction, and I want to have some kind of direct sum decomposition of C into A and B. So let's first do this direct sum decomposition. So I claim that we have C is going to be the direct sum, internal direct sum of the image of F and the kernel of this retraction R that we've been given. Okay, so the kernel of R is a submodule of C, and the image of F is a submodule of C, and this should then be a direct sum decomposition. So let's first prove that. So we write the little c as F of R of C plus C minus F of R of C. So obviously this is equal to C, but then clearly this part is in the image of F, and I'm claiming that this will be in the kernel of R. Okay, let's compute R on this. R of C minus F of R of C. Well, it's homomorphism, so this will be F R of C minus R of F of R of C. But we've been assuming that R after F is the identity on A, so that means that R of C is in A, and then first applying F and then doing R, there's nothing in total. So this will be R of C minus R of C, and indeed this is 0. Okay, so this is indeed in the kernel. So that means that C is at least a sum, internal sum of the image and the kernel. Everything can be written using two components like this, but then it has to be direct sum. So suppose that C is in the intersection, so the image of F intersected with the kernel of R. Well, then we have to show it's going to be 0. Well, let's say what we know. Then C is of the shape f of A for some A in A. This is in the image. And well, let's see what happens if we apply the other condition that we have. It's in the kernel of R. So 0 is R of C is going to be R of F of A. C equals F of A. And again, R after F is going to be the identity of A. So this is A. So can be A is 0. And of course, if A equals 0, then C is 0. So indeed, the intersection is going to be only having 0 as an element. Okay, so what you now have is that my middle component here has been decomposed into the image of F and the kernel of R. And now we have well, the image of F. So of course F will surject to its image. But this entire map is an injection because of this 0 here. So that means that this is just an isomorphism with A under F. Again, as R modules. And I can actually also look at its kernel of R. I'm claiming that this is now going to be isomorphic with B via G. Okay, so why is that? Well, if I look at my direct sum and I am going to apply G, the kernel of G is exactly the image of F because we have short exactness. So this guy will disappear. And the image of G is entirely determined by this component, by this submodule. So, okay, so kernel of R and the whole of C will have to have the same image, and this was surjective, so kernel of R maps surjective onto B. On the other hand, what could be the kernel here? Well, the kernel of G on this entire thing, on C, is exactly the image of F, which is standing here. Now, if I restrict my map G to this guy, then the kernel of this restriction will be this guy here, intersected with the kernel of G, but that was this one. Okay, so the kernel of G restricted to the kernel of R, or the kernel of, sorry, the restriction of G to this guy has kernel, and the section of this guy with intersection of this. And we've just been showing that's going to be 0. Okay, so let me summarize this because the kernel of G equals the image of F. You have to write something down, but again, I don't want to spend too much time writing down the details, so just go through them. Anyway, so that gives you this one, and therefore we now have identified that this guy is isomorphic to A direct sum B. So C is isomorphic to A direct sum B, because that was the image of F and the kernel of F, and both are isomorphic to respectively A and B. Okay, so that's how far I got with this, and then I'll leave it to you to check that if I have my isomorphism C that I've just been constructing, so basically this part of A in here corresponds to F, and this part of B in here corresponds to G. That's more or less what it says. And then I leave it to you that indeed this diagram that you then write down, because this isomorphism does commute. So check. So the diagram on the left does commute. Using those maps. So everything is going to be an R module morphism, and that will be then A implies, sorry, C implies, excuse me, well, A implies C. Okay, and then B implies C is done in a similar way, but in that case he knows something about G. G has a section, and it's a good exercise to modify the construction, but again you're going to use this as to have a decomposition of C, and then you go about it in a very similar way. Again, it's a bit annoying to have to do it, but it's also a very good exercise to really sit down and introduce a notation and write down a little bit more than I did here. But this kind of mathematics you really have to do in order to absorb it. Okay, that is one topic. And